The final topic we're going to take a look at is being able to work with multiple linear regressions. So first of all, let's define what a multiple regression is. Multiple regression can have many variables, but a pretty simplistic form is when we have two inputs, let's call them x1 and x2, and we get one output. The example that I have is the amount of dissolved oxygen concentration in water, which would be the y, given the temperature, which could be x1, and the concentration of chloride in water, which could be x2. And then there's a constant a naught, similar to the constants that we had with linears and quadratics. So just like before, we can derive the formula for, and the matrix, when I say formula, I mean the system of the matrix, let's say that y is going to be equal to a naught plus a1 x1 plus a2 x2 plus e, where e is that residual, just like the other one. And we'll skip a few steps because we've already seen this a few times. We can solve for the sum of those squares to get something that fits this form. And then just like before, we can take the partials of a naught, a1, and a2 because that's what we're trying to solve for. And then optimizing those, we can just go ahead and distribute back through and solve for anything that contains a y. And we get this formula right here. So n is the number of ordered triples in this case, for if it's going to have three variables within it. And then x1 and x2 are going to be the respective inputs or the independent variables. Y is going to be the dependent variable. Okay, so this is our formula, derived the exact same way as before. And so let's just take a look at an example of how to implement this matrix formula. And we're not going to use Excel this time. We're just going to go ahead and use MATLAB for everything. So I just wanted to show everybody a couple different ways, one of which being Excel. This time we're just going to use MATLAB for all the sums. Airplane simulator developed to simulate the distance required to stop for a newly developed aircraft. So the pilot sits in the simulator, and to be able to stop the plane, there's a time where you have to react, and then there's the time that the mechanic, the mechanism of the brake actually works. So basically what it's saying is that if you're going 45 kilometers per hour, there's 5.6 meters of traveled before thinking, and then braking is 5 meters. And as that goes up, then so do the other time, or so does the distance as well. All right, so we're going to write MATLAB code to find a multilinear regression of the form constant a1x1, a2x2 that explains speed as a function of thinking and braking. All right, so let's go ahead and hard code all of this stuff in first, all right, which is always the first chore that we should probably do. So I'm going to start by just calling y equal to 45, 87, 135, 200, 275, and 465. And then x1, I'm going to call 5.6, 8.5, 11.1, 14.5, 16.7, 22.4. And then finally, we have our x2 is going to be equal to 5, 12.3, 21, 32.9, 47.6, and 84.7. And we need to go through, we need to figure out several different variables. And let's take a look at our matrix formula. And so we need the sum of x1, the sum of x2. We know that n is going to be 6 because there's 6 ordered triples in this example. 1, 2, 3, 4, 5, 6. All right. But then we have to multiply the matrices and we have to square them. All right. So let's do this. Let's make a few more matrices. All right. We need one, let's just call it x1 squared. I'm going to call it x1 sq, and that's going to be equal to x1 dot squared. All right, so that's a new row matrix, and it's going to square each of the elements. We're going to do the same thing for x2. And then we need x1y. So we're going to call that x1y is going to be equal to x1 dot times y. And then we need x2y. And that's x2 dot y. And then we also, I think that's everything that we need. We can define n to be 6 if we wanted to hard code it in there. All right, so now let's go ahead and find the sums. All right, and usually we can use Excel to do this, but it's not a big deal. We can use MATLAB. So the sum of y is going to be equal to the sum of the y variables, or I'm sorry, the y vector. Sum x1 is equal to sum of x1, and then finally sum of x2, and these are the easy ones. So sum x2 is equal to the sum of x2. Now we need sum of x1 square. So sum x1 SQ is going to be equal to the sum of x1 x SQ. And I'm just going to copy this and just change all the ones to twos. All right. And then we need the sum of x1 y1. All right. And I don't think we found that. So let's go back up here. Oh, we did. Oh, no, we didn't. Excuse me. So let's call this x1 y or x2 is going to be equal to x1 dot times x2. All right. And sum x1 x2 is going to be equal to the sum of x1 x2. And now we can do the y's. Right, so we already have sum of y, so we need sum x1y is going to be equal to the sum of x1y. And then finally, let's just change the ones to twos. All right, so a couple semicolons to suppress. All right, and now we can create our matrix. All right, so let's call A. Now, what formula are we plugging into? Well, we're plugging into this formula right here. So we have n, x1, x2, x1, x1 squared, x1, x2, x2, x1, x2, x2 squared, and then equals the y, x1, y, x2, y. All right, so just plugging into this formula right here, and we already have all the variables. Right, so we have n already. Remember, we hard-coded n right here. We need sum of x1, and we need sum of x2. Okay, and now we need sum of x1, so this is the next line. We need sum of x1 squared, and now we need sum of x1, x2, semicolon, and now we need sum x2, and then we need sum x1, x2, and then finally we need sum x2 squared. All right, so that should take care of our matrix. Hopefully I didn't make any typos. And then for B, we need sum of y, semicolon, sum of x1y, semicolon, and sum x2y. All right. And now let's define R to be equal to A / B. All right, now I'm just going to run this because I've been typing a lot of stuff out here. So I just want to make sure I typed in everything okay. And these should be the coefficients. And this should be the constant. This is the coefficient of x1. This is the coefficient of x2. All right, so now we have no idea if this is right or not, but we're going to show you a way to check to make sure it is. So I'll say multi-reg for multiple regression is going to be equal to, now remember the first one is the constant. Okay, so that's going to be R1, 1 plus, and then this is going to be the coefficient of x1, so that's R2, 1 times x1 plus R3, 1 times x2. All right, now there's a little bit of redundancy here because x1 and x2 are already defined, right? Remember we defined them up here. So let's do this. Let's now clear x1, x2, and also let's make them symbolic variables. All right. The only thing that doesn't help with is if we wanted to plot this on a 3D plane, but we're not going to do that, so it's not a big deal. All right, so let's print f, and we're going to say the multilinear equation is %s All right, and that's multi-reg. It might be ugly. All right, let's see what happens if we run it. All right, so we get this hideous, hideous looking thing because it wants to put it into exact form, and does. All right. Now, how do we know that we're anywhere close to accurate with this? Well, what we can do is we can plug in 5.6 for x1 and 5 for x2, and hopefully we get a number close to 45. We could plug in 8.5 and 12.3, and we should get a number at least reasonably close to 87. So let's do that. Okay. So let's fprint f when x1 equals 5.6 and x2 is equal to 5, then y is %f. And what we're going to do is we're just going to compute this, except we're just going to replace x1 with 5.6 and x2 with 5. And we'll do this again for the other ones, but let's just go ahead, run this. All right, and we get 44.993622. And the actual value is 45. So now that might have just been lucky. So let's just try another one. Let's try the one for 135, which is 11.1 and 21. All right, so let's see how close we get with that one. But at least we're hopeful because we got a pretty decent output. So 11.1 and 21. So this is 11.1 and this is 21. All right, and let's just go ahead and execute that. And we get 134.92. The actual value was 135. So we're within it. We're accurate to at least the 10th place. So that's pretty good. Okay. If you wanted to try one more, just because we can, let's try the largest one. Because usually the further you go out, there's a little bit more error in extrapolation, 22.4, 84.7. Okay. All right, so 22.4, 84.7. If I was smart, I would have just said x1 parentheses 6, x2 parentheses 6. So, but I guess it's too late now. Now remember that value was 465, I believe, right? 465 was the actual value. 464.9798. So a couple of things is that one, the association is really, really good. And number two, the model that we developed is pretty accurate to be able to paste or to come really close to the multilinear model for this, to the original data. So pretty cool that we're able to do this. And that ends our discussion, or at least our lecture, on being able to work with linear regressions, quadratic regressions, any sort of polynomial regression, and multilinear types of regressions.